Welcome all. Myself Jissa David, Assistant Professor, Department of ECE, Rajagiri School of Engineering and Technology. This lecture, I am going to discuss the topic number representation and its arithmetic operations from the subject Logic Circuit Design under K2 syllabus. It includes binary number representation, arithmetic operation of binary number, octal number and hexadecimal number, then fixed point number representation and floating point number representation. Let's start with binary number representation. It includes unsigned and signed representation. Signed representation, it is classified into signed magnitude form, 1's complement form and 2's complement form. The first one, it is signed numbers. Signed numbers are always positive. There is no sign bit in unsigned binary number, so it can only represent its magnitude. In 0 and 1, 0 is an unsigned binary number. The range of unsigned binary number starts from 0 to 2 raised to n minus 1, where n is the number of bits in the binary number. Let's see an example. Represent decimal number 39 in unsigned binary number. So first we need to find out the binary number of 39. For that, dividing 39 by 2, so we will get a remainder 1, then again divided by 2, we will get again a remainder, and this process is continue until the quotient become 0. And this is the binary number of the decimal number 39, and it consists of 6 bit. If you want to represent in 8 bit, we are adding additional 2 bit. So this is an 8 bit representation of decimal number 39. Next one is signed binary numbers. Digital system must be able to handle both positive and negative numbers. A signed binary number consists of both sign and magnitude information. Sign indicate whether the number is positive or negative. Magnitude is the value of the number. There are 3 ways in which signed numbers can be represented. First one is sign magnitude. Second one is 1's complement, and the third one it is 2's complement. Let us start with sign magnitude form. When signed binary number is represented in sign magnitude, the leftmost bit is the sign bit. If it is 0, that indicates it is a positive number. If it is 1, that indicates a negative number. The remaining bits are the magnitude bits. In the sign magnitude form, a negative number has the same magnitude bits as corresponding to positive number, but the sign bit is 1 rather than 0. Let's see an example. This indicates plus 25, the sign number plus 25. And 11001 is the magnitude of plus 25, and this is 8 bit representation. And the leftmost bit, it is 0, indicate this is a positive number. Then for minus 25, the magnitude remains same, but only change in the sign bit, it will become 1. So if it is 1, that indicates it is a negative number. So this is sign bit and this is the magnitude, and both the numbers, the magnitude remains the same. Next representation, it is the 1's complement form. In In the ones complement form, the positive numbers are represented the same way as positive sign magnitude numbers. So plus 25, this is the sign magnitude form, and its ones complement form is also the same number. But for negative numbers is obtained by inverting each bit of corresponding positive number. Let's see an example. This is plus 25, its magnitude form, and minus 25, its sign magnitude form, only change in the sign bit, and ones complement form is obtained by inverting each bit of this number. So we will get its ones complement form. In twos complement form, the positive numbers are represented same way as in the sign magnitude and ones complement form. But the negative numbers are represented by adding 1 to the LSB of ones complement of the corresponding number. Let's see an example. For plus 25, the sign magnitude form ones complement and twos complement, the representation will be the same. But for minus 25, sign magnitude form is obtained by simply change the sign bit to 1. Magnitude remains same. And to get its ones complement, inverting all the bits. So we will get its ones complement form, and its twos complement form is obtained by adding 1 to this LSB. So we will get its twos complement form by adding 1 to the LSB. So this is the representation in twos complement form of the number minus 25. This table indicate these are the binary numbers, and it is a 5-bit number. The leftmost bit indicate whether number is negative or positive, and this is the sign magnitude, and this is the ones complement and twos complement representation of corresponding decimal number. And from this you can see that in sign magnitude form, if you are considering a 5-bit representation, sign magnitude form, it can represent the numbers in the range of minus 15 to plus 15. Ones complement form also, it can represent the numbers in the range of minus 15 to plus 15 if it is a 5-bit. And for twos complement, we can represent the numbers from minus 16 to plus 15. So this is the general expression for the range of corresponding representation. Here it is 2 raised to n minus 1 minus 1. Here n it is, in this example it is 5. So 2 raised to 4 minus 1, that means 15. So minus 15 to plus 15. Here also minus 15 to plus 15, but in twos complement it is minus 16 to plus 15. And one more difference is that when you consider sign magnitude and ones complement form, for 0 it has 2 representation. This is one representation and this is another representation for sign magnitude. Similarly, in ones complement, it has 2 representation for 0. So that will be make some confusion that can be avoided by twos complement. In twos complement, 0 has only 1 representation. So normally we are using twos complement form. Now next is the general term, that is the radix complement. Here, r's complement of n digit number n in base r, it is equal to r raised to n minus n. Let's see with an example. The tens complement of the decimal number 2389 can be computed by using this expression. Here, r equal to 10, where r indicate the base, n equal to the number of digits in the number. Capital N is that corresponding number, and its tens complement is obtained by r equal to 10 raised to 4 minus this value, we will get 7611. And to obtain 9's complement of this number, just subtract it from 1, we will get the 9's complement of this decimal number. So these are the definition for radix complement. The r's complement of n digit number n in base r, it is defined as r raised to n minus n. And comparing with r minus 1's complement, that means the 9's complement, we note that r's complement is obtained by adding 1 to r minus 1's complement. So to obtain r minus 1's complement, we have to be subtract it 1 from 10's complement. So this is the corresponding example. Let's see a problem. Represent the following decimal numbers in the sign magnitude 1's complement and 2's complement form. Right, the first step is we need to be find out how do you represent plus 39 and minus 39 in this three form. For positive numbers, plus 39, its sign magnitude 1's complement, 2's complement will be the same. So first we need to be find out its binary number representation, and this is 8 bit. We need to be add additional 2 more bit. This is a 16 bit. We need to be add additional 2 more bits. So this is the representation of binary number of plus 39, and this is sign magnitude form, 1's complement and 2's complement form. It will be same for positive number, but for minus 39, the magnitude remains the same. We have to be change the sign bit, that means the leftmost bit. So it will become like this. Change this bit to 1 and the remaining bits are same. Now to get its 1's complement, taking 1's complement of this thing, inverting each and every bit. So we will get, this is the 1's complement form of minus 39, and to get 2's complement, simply adding 1 to the LSB of this number. So this is the answer. Second question, determine decimal value of the signed binary number expressed in sign magnitude. So this is the number, and here we have total, it is a 8-bit number. So the 7-bit represent its magnitude, this bit represent its sign. So to find out its decimal number, we are considering the 7 bits. So we need to be find out its decimal value. So this is its decimal value. Since the leftmost bit it is 1, the number is negative. So this is the corresponding decimal value. Next we are considering arithmetic operations of binary, octal and hexadecimal number. We'll start with the binary arithmetic. It is essential in all digital system. To understand digital system, we must know the basics of addition, binary addition, binary subtraction, its multiplication and its division. Let's start with binary addition. Let's see its rule. 0 plus 0, it is 0. 0 plus 1, it is 1. 1 plus 0, it is 1. 1 plus 1, it is 0, and with a carry of 1. We will see one question. Add this binary number. So when you add these two number 1 plus 1, it is 0 with a carry of 1. So 1 plus 1, it is 10. 10 plus 1, 11. So 1, and there is a carry, again 1. Again 1, carry 1. So this is 0, again carry 1. So this will be 1, 1. So this is the binary addition. Next one is the binary subtraction. Let's see the rules. 0 minus 0, 0. 0 minus 1, it is 1 with a borrow of 1. 1 minus 0, 1. 1 minus 1, 0. Let's solve one problem. Subtract these two numbers. So here I am considering another example. You can take this as a homework. Now here I am considering, let it be this case. 1 minus 0, it is 1. 1 minus 1, it is 0. 0 minus 1, 1 with a borrow of minus 1. So it will become 0. So this will be the answer. I am considering this as the example. Then these are the few questions. Now the third one is binary multiplication. This is the rule. 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, it is 1. Example. I am considering this number. I am going to multiply these two numbers. When you multiply 1 with this number, we will get the same number. Again, I am multiplying with 1, we will get the same number. Multiplying with a 0, all the bits will be 0. Again, all the bits will be 0. Again, multiplying with 1, we will get the same number. And adding this all number according to rule of binary addition. So this will be 1. This will be 1, this will be 1, this will be 0 with a carry 1. And this is 1 plus 1, 1 0 plus 1, 1 1, 1 1 plus 1, it will be 1 0 0. So 0 will be here and there is a carry of 1 0. So here it is 1 1, so carry 1, 0, carry 1, 0, carry 1. So this will be the answer. You can do these examples. Now next one is the binary division. Consider, we need to divide this number with this. So it will become like this. Then subtract. This will be 1, 0, 1. So we are considering the next bit. So here it will become 1. Then again subtracting this 0, 1. Again we are considering the next bit 0. So here it will become 0. Then again we are considering the next bit. It will be 1, 1. So the remainder will become 0. So this is the quotient 1, 1, 0, 1. You can go through these examples. Now for arithmetic operation with the signed numbers, we are considering normally 2's complement form. It includes 4 cases when you consider sine number. The first case is both numbers are positive. So the sum is positive, therefore it is a true binary. I am considering these two numbers plus 12 and plus 14. We need to add these two numbers. So this is the corresponding binary representation, and this bit indicate the number is positive. Going to add this number 0, 1, 0, carry 1, 1, carry 1, and this will be the answer. Second case, positive number with a magnitude larger than negative number. So here final carry bit is discarded. So here if there is a carry bit, that indicate it is a positive number. Let's see, we want to add plus 15 and minus 11. And if there is any carry, the sum will be positive and we can discard that carry bit. So here we need to be consider its 2's complement form. Plus 15, it is the same. For 1, 1, 11 plus 11, it is represented by like this. I am considering 5-bit representation. Then minus 11 in 1's complement form, it is represented by like this, inverting all the bits. And its 2's complement form, it is represented by just adding 1 to the LSB. So we will get this number, and we are adding these two binary numbers. 0, carry 1, 0, carry 1, 1, carry 1, 0. So here you can see that there is a carry, and we can discard this carry, and this is corresponding to the number is a positive number. Carry discarded, that indicate is a positive number, and you can see that plus 15 plus minus 11 actually it is 4 plus 4, and you can see this is the binary representation of plus 4. Third case, negative number with a magnitude larger than positive number. So here the carry will be 0. There is no carry. So that indicate the number is negative. If the number is negative, the final answer is obtained by take its 2's complement form. So here we are going to add plus 11 and minus 15, and its magnitude is larger than this number. So this is the corresponding binary representation, and plus 15 is represented by like this. With its 1's complement form, it is represented by like this, inverting all the bits, and its 2's complement, it is represented by adding 1 to the LSB. Now we are considering these two numbers. We are going to add these two numbers. 0, carry will be there. Okay, so you can see that there is no carry. No carry means the number is negative number. So that we need to find out its 2's complement. So inverting this bit, so it will become 0, 0, 0, 1, 1, then add 1. So take its 2's complement because final carry is 0. So the number is negative. So take its 2's complement, we will get this is the number. So when you add these two, actually we are getting minus 4. So this is a negative number. and its magnitude is given by 4 and its binary number it is 00100. Let both numbers negative. So both numbers are negative. Final carry bit is discarded. The sum is always here. It is negative. So therefore the final answer should be represented in 2's complement form. We need to find out its 2's complement form of 1 1 and 1 5. This is 1's complement form and its 2's complement form is this, and minus 50 its 2's complement is given by then next we need to add these two numbers 0 carry 1 1 so there will be a carry. So this carry can be discarded and both the numbers are negative. The sum is negative and take its 2's complement. So this will be the final answer. Actually this is the binary number of 26 and this is a negative number, so it is corresponding to minus 26. You can consider this as an examples. Then for octal and hexadecimal arithmetic, which is almost similar to binary arithmetic. So arithmetic operations can be performed by converting octal or hexadecimal number to binary numbers and then using the rules of binary arithmetic we will get the answer in binary form, and that binary form can be again converted back to either octal or hexadecimal. In generally number system it includes integer number as well as a fractional number. So in integer number, which is represented as unsigned numbers or signed numbers, it can include signed magnitude form, 1's complement form and 2's complement form. But what about rational numbers or fractional part? For an example 2.5, 0.75. So the rational numbers in computer can be represented two ways. One is fixed point number representation and the second one is floating point numbers representation. In fixed point number representation, the representation as fixed number of bits for integer part and for their fractional part. The binary point is not stored anywhere. A format where binary or decimal point is fixed between two groups of bits is called fixed point format. There are three parts of fixed point number representation: signed field, integer field and fractional field. This is the case for unsigned numbers. It includes integer and fraction, signed fixed point integer, signed integer and fraction. And this is the corresponding range for signed representation, 1's complement and 2's complement. Let's see an example assuming the number is using 32-bit format. 1 bit for sign, 15 bits for integer part, 16 bits for the fractional part, and this is fixed for this case. Next we want to represent this number minus 43.625. where 0 is used to represent plus 1 is used to represent minus. So this is a negative number. It's a negative number. And when you consider 43, and this is we need to be represent integer part 43 with a 15 bits. This is the 15-bit binary value for decimal number 43. This is 16-bit binary value for the fractional 0.625. We are adding additional bits here, so that its fixed point representation, it is given by, this is sign bit, and this is integer part, and this is the fractional part. And the disadvantage, it is its limited range of values that they can represent. Inadequate for numerical analysis. It does not allow enough numbers and accuracy, because here the number of bits used for integer part and fractional part, it is fixed. And this is the, for a 32-bit case, this is the representation for smallest number, and this is the case for largest number. And the next one is floating point number representation. This representation does not reserve a specific number of bits for the integer part or fractional part. That is the advantage when you are considering floating point number representation. It includes 3 parts. The first part represents signed fixed point number called mantissa. The second part includes exponent. Third part, it is the sign bit. This is the representation. Let's see an example. Here also I am considering 32-bit format. 1 bit for sign bit, 8 bit for sign exponent, 23 bits for the fractional part. The leading bit 1 is not stored, as it is always 1 for the normalized number. Let's see an example. We need to be represent this number minus 53.5. So first we need to find out its binary number. And this is the binary representation. 53 is represented by like this, and 5.5 is represented by like this, and we are going to normalize this. So with a weighted position, it is 2 raised to 5. So this is the leading bit, which is represented as following below. And this is the exponent. For exponent, it requires 8 bit. So this is the 8 bit binary value of the exponent value plus 5. So this is the corresponding range. Since it is a negative number, so sign bit will be 1, and here it is. No need to store this number. This is a normalized one. The leading bit 1 is not stored. So here we are storing the exponent part. That means 5 is represented here with the 8 bit. Now the magnitude part. The mantissa part, we are using the 23 bits for the fractional part. This is the fractional part. With the 23 bits, so we are adding additional 0. So this is the floating point number representation. Thank you.